Oh, okay. Rachel looks like the only one here so far. You can get a private lecture here. Yeah, I got your message. No worries if you have to leave. Yeah, no, do what you got to do. All right, maybe there'll be some more showing up, but I will. Oh, we got one more. All right, we're on the roll. Okay, how you doing, Molly? Uh, where were we? All right, we were on chapter 14, slide 18. I will go to that, and we'll probably finish chapter 14 today. And chapter 15 is like extremely short, and so probably knock that out, maybe even today. Okay, we'll see. We'll see how it goes. All right. Any questions before I begin?
I have a quick question.
Sure, go ahead.
About chapter 13. I'm
Yes.
having trouble with some of the homework questions that are asking me to convert, like if you're given an amount of gas and it reacts at STP, how to find the mass of a solid element that's gonna be needed to react.
How to find amount
Yes,
of
like this question that I've been stuck on, I've tried it a couple times, but I can't get it right, is if 3.75 liters of oxygen gas react at STP, what mass of solid iron is needed to react with it?
Okay, so let me write this down. 3.1, 3.7,
3.75 liters of oxygen gas.
okay, liters of O2. Okay. And it's the reaction is between oxygen and iron.
Yeah.
And the product, is it iron 2 oxide or is it
Iron 2 oxide, yeah.
Okay, so first thing first, let's make sure we got it balanced. All right, we got that. Okay, so if you use 3.75 liters of oxygen gas, the question is how many grams basically of iron are needed for this reaction to proceed, correct?
Yep.
Okay. All right, well, let's do that. Let me share the whiteboard here. And correct me if I'm wrong as far as what the question has. All right, let me get my stuff out of the way. All right, so the first things first is we write down the reaction. And based on what you said was that oxygen in the presence of iron react to give you iron 2 oxide, correct?
Yeah.
Okay, so we got to balance this first because we're going to need this. And so it looks like you got 2 oxygens on the left, 2 on the right. Okay, now that kicks up our iron scenario. So we got to put a 2 in front of iron. And so now we're balanced. Okay, so the question here was we are at STP. And being at STP means that we can use a 22.4 liter per mole relationship. Okay, so we keep that to the side. Now, if we start off with 3.75 liters of O2, the question is, how many grams of iron do we need? Is that correct?
Yeah, and then on this one, the product is Fe2O3.
Oh, okay, so it's a different,
It's not iron oxide, it's
what?
something else.
What? This is iron 2 oxide, that's why I say iron 2. So Fe2O3?
Yeah.
Okay, which means this is iron 3 oxide. This one up here was iron plus 2. And this one here is iron 3. Okay, which means that changes let's do this here. Let's change all this. It's totally different ball game. Wow, the calculations are the same. Okay, what differs is that mole ratio between it. So we got to make sure that's why it's important that we get the right reactants here. So it's iron 2O3. So this is iron 3 oxide. All right, so to balance this, we got 3 oxygens on the right. That's a 3. That's supposed to be a 3, but let me clarify this here a little bit. Okay. All right. And so we got 2 oxygens on the left, 3 on the right. So what we could do is find a common number, right, to balance it. So what common number do we have between a 2 and a 3?
A 6.
6. So we can put a 3 here. That gives me 6 oxygens, and put a 2 here, which gives me 6 oxygens. So the oxygens are balanced. Okay. And in the process of doing that, that kicks up my iron to 4, so no problem. We go over here and put a 4 in front of oxygen. Excuse me, iron. So it looks like we're balanced. You got the mole ratio is 3 oxygens, requires 4 irons to give us 2 molecules of iron 3 oxygen. Okay. Now it doesn't change the question. The question's the same. We just have to make sure that we have the right, correct, balanced chemical equation. Because if you notice before, if we had a product, and like I had originally, you said iron 2 oxide, that's why I wrote this down. And then I put a 2 here and a 2 here. Notice the ratio here, this is a 1 to 2 ratio. And up here is a 3 to 4. Totally different ballgame, right? Which is important when we transfer from the moles of oxygen to moles of iron. Okay? So point number 1, make sure you got the correct products. Make sure you got the correct balanced chemical equation. All right. Step number 1, we write down what we're given. We are given 3.75 liters of oxygen. What are we looking for? Way over here. And we'll move this out of the way here. Oh, we got one more. Okay, those of you that just showed up, we're going over a question, one of the homework questions. What number was this? Was this Rachel?
It was question number 6 on homework for chapter 13.
Okay, chapter 13, question number 6, which stated the oxygen in the presence of iron reacts to give you iron 3 oxide. Okay, now the key part about this reaction is to make sure that originally we had it written like this, but it's the wrong product. It's right. It's the wrong reaction. That is a correct product, iron 2 oxide. But notice the mole ratio is totally different. It's a 1 to 3 between oxygen and iron compared to 3 to 4 with the iron 3 oxide. Okay. So we got to make sure we have the right balanced chemical equation. All right. So as with any problem, we write down what we are given. Okay. And write down what we're looking for. We want to figure out how many grams of iron we need for this reaction. Very analogous to the reaction that we were doing yesterday in the lab, where we have hydrochloric acid and the metal. I'm having a senior moment with the metal, so we're doing the calculations to figure out, who was the limiting reagent. So what we're doing here is trying to figure out if we start off with 3.75 liters of iron, okay, how much iron, 3.75 liters of oxygen, how many grams of iron do we need? Okay, that is the question. So, and we are at SDP. So the first thing is we write down what we're given. which is liters. And if with any problem, we can't work with liters, nor can we work with grams to go from grams to grams or liters to grams or liters to liters. We need to convert to moles, okay? So the very first step you got to do is convert to moles. Since we are at STP, we can use the relationship of 1 mole of oxygen gas has a volume of 22.4 liters, okay? Notice that our liters cancel out. So with it, at this point, if you did the calculation, you would know how many moles of oxygen you would have, okay? But we're not where we need to be. We need to be 2 grams of iron. So the next coefficient that we utilize, or ratio, is the ratio of oxygen to iron, which is we want oxygen in the denominator and iron on top, okay? And then we put the coefficients, which is 4 irons to 3 oxygens. At this point, notice we cancel out the units of oxygen, okay? Hold on 1 second. And so at this point, if you do the mathematics, we end up with moles of iron, okay? So notice that we start off with liters of oxygen, went to moles of oxygen, and now with the stoichiometric relationship between iron and oxygen, we are now at moles of oxygen, okay? Well, the question again is that we will need to get to grams. Okay, so our final coefficient here, or conversion factor, is we look up the atomic weight of iron, which is 55 point, looking that up, 85 grams of iron for 1 mole of iron. Okay, and notice we cancel, keeping track of our units. Our moles of iron cancel, leaving us with grams of iron. So now you got the problem set up properly. The mathematics is left up to you. So it's 3.75 divided by 22.4 times 4 divided by 3 times 55.85 grams. That would tell you how many grams of iron are necessary for this reaction. If you start off with, let me get my calculator here real quick. I got 3.75 divided by 22.4, okay, times 4 divided by 3, okay, times 55.85. Okay, I got 12, keeping track of my units, 12.5. I got 12.5 grams of iron. Check my math, okay? Keeping my sig figs, I got 3 sig figs and 3.75. Don't forget the 22.4 could be a factor in sig figs, but it's got also has 3. So my answer should be in 3 sig figs. So what this tells me is that if I start off with 3 3/4 liters of oxygen, I require 12.5 grams of iron for this reaction to proceed. Okay?
Okay, thank you.
Yeah. The key takeaway is this: the fact that you're at STP, you need to convert that volume of liters into moles. Occasionally, the question asked is, they give you the volume in milliliters. Well, all right, convert the milliliters to liters and then use this factor. You can either convert the volume you're given, if it's in milliliters, or convert that conversion factor of liters into milliliters. Either one, you got to get to moles, okay? All right, any questions? All right.
Does that say 55.85 grams of iron toward the end of that problem?
No, that's the atomic weight of iron. You find that from the periodic table.
Atomic, wait, the grams of iron?
You're breaking up. It's
The grams of
per mole.
iron? Okay, thank you.
Yeah, it's 55.85 as per the periodic table. Yeah, 55.85 grams. All right. Any other questions? Okay. All right. Bear with me for a second. I have to answer this phone call. It's quite important. So give me about 5 minutes. And I'll be right back. Let me stop my sharing for a moment. Okay, I'm back. Oh, sorry, I wasn't muted, so you heard all that, huh? Yeah, a little bit of problem with my late white student loan. Okay, where was I? Okay, so we were here and we were talking about IMF, intermolecular forces. Okay, recall that there were 4 forces, intermolecular forces, and these are forces intra, okay, intra and inter. The difference between inter and intra. Inter are forces that molecules have with other molecules, okay? And intra are basically what molecules have, the forces that keep the molecules together within the molecule, okay? We have 4 forces. The first one was London dispersion forces, which dealt with molecules that were nonpolar, okay? Then we had dipole-dipole forces, which dealt with molecules that were polar. And then we have London breaking forces, which dealt with molecules that were polar, however, very specific polar molecules, and that is hydrogens that were bonded to nitrogen, oxygen, or fluorine only. Yes, they are a dipole. It is a dipole interaction, but it's a special dipole, which is a little bit stronger than just a standard dipole-dipole. And then finally, the last force, which actually dealt with ionic compounds and aqueous systems. So, and that is just, again, ionic compounds with aqueous systems that really could not use that force to kind of correlate with the other 3 forces. It's like a separate entity in itself. Yes, the question Rachel has is if the elements are bonded together, such as H2, which is hydrogen, are these London forces? So any compound that is nonpolar, would have London dispersion forces associated with it, okay? So like all the diatomics, like hydrogen, all the diatomics, remember, have no fear of ice cold beverage. Those diatomics, because you have 2 elements that are bonded together that are the same, there's equal pulling between the 2, okay? Equal pulling between the 2. And as far as the electronegativity, and the electrons are being shared, okay? So that means equal sharing. That means it's not a dipole, and therefore that means the only force associated with them is London dispersion forces. Now, when the molecules that are bonded together are not the same, like hydrochloric acid, HCl, we got 2 atoms that are not the same, there's always going to be one that has a higher electronegativity. And remember, when they have a higher electronegativity, that molecule is going to pull the electron density onto itself much more than the other one that has a lesser electronegativity. That results in a permanent dipole. Okay, so that is a polar molecule. Now, if the molecule is polar and the dipoles in the bond do cancel out, we end up with a nonpolar molecule. For example, we talked about carbon dioxide. Carbon dioxide has two polar bonds, a carbon oxygen going to the right, carbon oxygen going to the left, because the Lewis dot structure shows that it is a linear molecule. Well, that means that because they cancel each other out, even though it has polar bonds, that means that it is a nonpolar molecule. So now its force is simply a London dispersion forces. Okay, so we have to define the polarity of the molecule before we can assign to it the forces. And so that takes you back to Lewis dot structures to figure out, all right, is this molecule polar or nonpolar? And once you define that, then you're able to assign to it a particular force, and then we can do comparison. All right. So if we look at this this question here, to answer these type of questions, I think we did go through this one, but I'm gonna go through it again. This slide, that what holds the atoms together in one ammonia NH molecule, NH3? We're talking about one ammonia molecule. So we're looking at the bonds between nitrogen and hydrogen. So it's being asked, what's holding those bonds together? Well, they are polar covalent bonds. Okay, they're covalent bonds because they are two nonmetals bonded together, the nitrogen and the hydrogen. And then they're polar because the electronegativity of nitrogen and hydrogen is different. So we have polar bonds. Furthermore, when we do the Lewis dot structure, we'll see that ammonia ends up with lone pair on the central atom, okay? Lone pair on the central atom. And that's, double check here, make sure we are. When we end up with a lone pair, and this is what we have, nitrogen, hydrogen bonded, and then we end up with a lone pair on the central atom. We call that, when we were dealing with Lewis dot structures. All right, with lone pair, that means automatically polar molecule, okay? So we have covalent bonds between nitrogen and hydrogen, but they're polar because of the electronegativity difference between nitrogen and hydrogen. And then coupled on top of that, we have a lone pair on nitrogen, which makes it a polar molecule. What is holding the sodium ions in water? Okay, well, it's none of those first three forces, intermolecular forces, because in those first three intermolecular forces, we're dealing with covalent compounds. This question says we have a sodium ion, which means you're dealing with an ionic compound, and you're dealing with sodium ions in water. So the only force that's involved here is the ion dipole force. Okay. What is holding three HCl molecules together? All right, so now we're looking at forces that are holding three of them together. So we're looking at intermolecular forces. We have to define HCl. HCl is a polar molecule, okay? And then the second aspect is this. We see hydrogen here. So being a polar molecule, we can eliminate London dispersion forces as being involved here. And since we're not dealing with any ions, we can eliminate the ion dipole force. So what's left is a dipole force or a hydrogen bridging force. Well, let's take a look at the hydrogen bridging force. Why? Because we have hydrogen here. Remember, for hydrogen bridging forces, it is only pertains to those molecules that have hydrogen bonded to nitrogen, oxygen, or fluorine. This is not the case here. This is hydrogen bonded to chloride. Therefore, the only force left over is a dipole force, okay? What is holding the ions together in salt, sodium chloride? There's no mention here in this question about an aqueous system, so we're talking about solid out of an aqueous system. So we know that sodium and chloride are ionic compounds, okay? Because we got a metal and non-metal. So what's holding them together is ionic bonds, okay? What is holding four H2O molecules together, okay? So let's break it down. They're asking the question we're talking about. Four H2O molecules together. So again, we're dealing with intermolecular forces, okay? H2O is extremely polar. And if you do the lowest dot structure on that, you end up with, oh, where do you go? Come here. Oxygen bonded to two hydrogens, but more importantly, guess what? We have two pair of lone pair of electrons in the central atom. That even makes it even more polar. So water is, without question, always polar. Very polar. It's the most polar molecule that's out there. Okay. All right. So for that process, for this question, we can eliminate London dispersion forces. Okay. And we're not dealing with any ions here. So we can eliminate the ion dipole force. That leaves us with dipole and hydrogen bridging. Okay. Well, here we do have hydrogen bonded to oxygen, which is one of the three atoms that give the force is hydrogen bridging. So what is holding four H2O molecules together is hydrogen bridging. Okay. Notice when I'm reading through these questions, I'm going through a process of elimination. Okay, that's what I'm trying to emphasize. So you don't, if you may not know what the answer is just by looking at it, break it down into individual things that you do know. And then by process of elimination, you come up with the answer, okay? What holds nitrogen gas molecules to each other, okay? So we're talking about molecules that are being, gas molecules that are holding, they are being attracted to each other, being held on to each other, which means intermolecular forces, okay? So nitrogen gas, which is diatomic, means we have a nonpolar molecule. Since we have a nonpolar molecule, the only force that you can assign to it is the London forces, okay? This is like the previous question asked about hydrogen, H2. All the 7 dipole molecules, their forces are simply London forces because they are nonpolar. Okay, what is holding the oxygens together in an oxygen gas molecule? All right, so now they're wanting to know about the oxygens within a gas molecule. So we're not dealing about intermolecular forces, we're dealing with intra. Okay, so intra means what's holding the oxygens together. It is a nonpolar, again, oxygen's diatomic, so it's a nonpolar covalent bond. And then what is holding two ammonia molecules together? Again, here's the structure still up there in the right-hand corner. We're dealing with a polar molecule. We're dealing with two molecules, so we're dealing with the intermolecular forces and not the intra. Okay, so intermolecular forces, we go through the process of assigning what force, and it's not London dispersion forces because ammonia is very polar, and it's not ion dipole because there's no mention here of aqueous systems and ions. So that leaves dipole or hydrogen bridging. Okay, since we have hydrogen bonded to nitrogen, which is one of the 3 elements that hydrogen is bonded to that is assigned to it hydrogen bridging, the force we have here is hydrogen bridging force, okay? All right, so what we went through here in this series is looking at the questions, make sure, identify, are we talking about within the molecule or we're talking about with molecules outside, okay? Inter forces or intra forces. All right, any questions about that part? I kind of summarize the IMF here is obviously we're dealing with covalent compounds. And if it's nonpolar to the left, it just automatically reassigned to it the London IMF, okay? If it's polar, it depends. If it's polar, dealing with water, and you're talking about an ion, okay? And that's why we have this down here at the bottom. If we're, because water is polar, okay? And then if the question talks about an ion, like the sodium, the chloride, and ionic compound, then the only force it has is the ion dipole, okay? Now, if it's covalent, we're dealing with either dipole or hydrogen bridging. Well, remember that with hydrogen bridging, it deals with hydrogen bonded to either nitrogen or oxygen or fluoride, okay? That being the case, then the intramolecular force associated with those molecules when they're interacting with other of the same molecules is hydrogen bridging. That means all the others are simply dipole, okay? Now, the other aspect about the first three, the London dispersion forces, the dipole, and hydrogen bridging, is the strength of that interaction. The London dispersion forces have the weakest force, and the strongest force is the hydrogen bridging with the dipole somewhere in the middle, okay? That's good to know because once we take a molecule and we do compare and contrast between two molecules, we're going to be looking at some physical properties of these molecules and be able to predict who has, for example, a higher boiling point. Now, we won't be able to predict the absolute value of the boiling point, but we can do a relative comparison between two molecules. And we do that by assigning an intramolecular force to that molecule and then understanding that the weakest is London dispersion forces and the strongest is hydrogen bridging force. That information then allows us to determine who would have a higher boiling point, for example, and some other physical properties, okay, like these. Okay, some of the physical properties that we're going to look at is called vapor pressure. Well, vapor pressure is, for example, if you have a soda pop container with the cap on, okay? If you look at that soda, I don't have one here with me, but if you have a soda pop, let me see if I can. Okay, let's say I got an Erlenmeyer flask, and this is supposed to be my crude picture of Erlenmeyer flask, and I got it capped, okay? And I got a liquid in here, okay? Now, here's the liquid down at the bottom, and then up on top, I have an empty space, okay, of vapor that's in that empty space. If I had a pressure sensor right here in the empty space, I can actually measure a pressure. This is what we call vapor pressure, okay? Your soda pop, your capped, closed soda pop, in that clear space, there is a pressure, and that's called vapor pressure, okay? Boiling point, well, that's simply the temperature in which a molecule goes from the liquid phase to the gas phase. Water, for example, has a boiling point of 100 degrees, okay? Then we deal with surface tension, and that is how a liquid interacts with a surface. If you have a high surface tension, you can put a liquid on the surface and it would bead up or it would flatten out, okay? And viscosity. Viscosity is the thickness of the liquid. We know that water and honey, for example, that honey is very thick. It's very viscous. Okay, it has a high viscosity compared to water. Okay? Now, all of these properties, physical properties, are dependent on the intermolecular forces. Okay, for example, to viscosity, when you compare the viscosity of water compared to viscosity of honey, well, the fact is we know that honey flows much slower than water. If I had a cup of each and I empty the cups, well, that honey is going to take a little time to completely empty from that cup because it's thicker. It's more viscous. And it's more viscous because the molecules of the honey are holding on to each other much tighter than the molecules of the water, which results in the viscosity getting increasing for the honey. Okay. And because that tells you that the intermolecular forces for the honey molecules is much stronger than that for the water. Surface tension, the same thing. If I put two liquids on the surface and one of them beads up compared to the other liquid that flattens out, well, the one that beads up tells you that, again, the molecules of that liquid have a higher intermolecular force because they're holding on to each other much tighter. Okay? You've seen the boiling point when we did the experiment. You see that we had a flat line in our heating graph where we took ice and we melted it. Remember that experiment? And then eventually when we got the water to boil and it was boiling off, we had a flat space, okay, a flat plateau where the temperature did not decrease even though it was still picking up energy. Well, what is happening there is when the liquid is absorbing that energy you put into the system, what it's doing is breaking up that intermolecular force between the molecules to cause the liquid to go into the gas phase, okay? If that force is strong, it's going to take a higher temperature to boil. Water boils at 100 degrees Celsius, so it takes a lot of force and energy to break up that liquid to go in the gas phase. When we compare it to, say, alcohol, which boils around ethanol, for example, boils around 78 degrees, the temperature is much lower, which suggests that when I compare water with alcohol, the intermolecular forces of alcohol is much less because it has a lower boiling point. So it takes less energy to drive the molecules of alcohol away and kick them into the vapor phase. Okay? They're all related to intermolecular forces. So you can see how important it is. If we're going to do compare and contrast, we have to assign an intermolecular force to the molecule, and then based on the strength of the IMF, be able to determine relative vapor pressure, boiling point. Now the vapor pressure is, like I stated, is shown here. Now, if these molecules that are in the liquid, which I'm just going to draw circles, if they are held on to each other, hold on to each other tightly, then we're going to have less molecules in the vapor phase. Okay, but if these molecules don't have a weaker intermolecular force, there's going to be a lot more gas molecules in the empty space, and their vapor pressure goes up. Okay, things that are very volatile, for example. That's why things like fingernail polish remover. You know, as you uncap that thing, you can smell it. It just comes right out. You know, it just is very volatile. That suggests that the intermolecular forces for the molecules of the fingernail polish remover are not very strong compared to, say, water. And if I have a container of just a fingernail polish remover and water and just open container, the fingernail polish remover will evaporate much quicker than the water, because it doesn't take much energy for the fingernail polish remover to evaporate, because it's very volatile. Okay, which is related again to the intermolecular forces. All right, so vapor pressure, as I talked about, that is the amount of energy, kinetic energy, to break the intermolecular forces, okay, in the liquid phase and go to the gas phase. Okay. And so obviously, and that happens spontaneously too. you don't have to put energy into the system. I'm sure you left a container or a glass of water on the kitchen top and forgot about it for a few days and came back and it evaporated. Some of it evaporated on its own. Did you put heat into it? No. Well, that's because the molecules are moving. And what happens is when they move on their own, some of them have enough kinetic energy to escape the liquid phase and go into the vapor phase. And with time, that happens to all of them. Eventually that glass container just is totally dry. Okay. But in the meantime, if you put energy into the system, you can do the same thing and expedite that. But you have to put energy into the system. All right. Now, if you put no lid in a closed container, no lid in a container of liquid, everything's going to eventually evaporate. But if you put a cap on it, then we got what we talked about, the vapor pressure. Okay. So when we look, the vapor pressure is the pressure exerted by the gas molecules above a liquid in a closed container, as that picture I drew earlier. Now, if we have strong IMF, we would expect to have a lower vapor pressure, okay? That means that stronger attractions would mean that less molecules will go into the gas phase. Okay? So stronger IMF, lower vapor pressure. And you can see here in this diagram, and the question is, which has a weaker IMF? And that would be A, because both of these, and let's assume these are closed containers. Okay, so on the diagram on the left, you can see there's more gas molecules in the vapor phase. There's more molecules in the vapor phase, meaning there's more in the gas phase. Okay, there's more circles floating around in the gas phase compared to B. Okay, what that suggests is that for A, the intermolecular forces are weaker and therefore require less energy to have them break apart and go into the gas phase compared to B. Okay, and because of that, A would have a higher vapor pressure because there's more gas molecules for A than they are for B. Does everybody see that? Okay. So again, that suggests that the intermolecular force for A must be weaker when we compare it to B. We haven't assigned anything yet. We're just doing some relative examples here to give you an example of high IMF and low IMF related to physical properties. Now, with respect to boiling point, the stronger IMF would result in a higher boiling point because the molecules are being held together tightly and will require more energy to break them apart. Okay, which is also true for for the melting point. You'll have a higher melting point. The melting point of something is that temperature in which a solid goes to the liquid. Boiling point is that temperature that a liquid goes to the gas. Okay, so if you have high IMF and we're going to compare it to something else that has lower IMF, that means the one with the higher IMF will have a higher boiling point / melting point compared to the other species you're trying to compare it to. Okay. With respect to surface tension, for the same reasons, a high IMF means that you have a high surface tension. And so if we were to, as I explained earlier, to put 2 drops of 2 different molecules, A and B, well, if you look at the A, the fact that it beads up more would suggest that it has a higher IMF, okay? because the molecules are being held on to each other much tighter than B. B, not so much, that liquid spreads out, okay? Viscosity, okay, oil we know that flows fairly slowly and it has high viscosity compared to, say, the alcohol vodka, very low viscosity, flows very rapidly, right? So a strong IMF, having a stronger IMF when we're doing a comparison, we would expect to have a higher viscosity, okay, because the molecules are being held on to each other tightly. And so let's do a comparison. So we have ammonia and we have fluorine. So before we do anything, we have to have the structure. We have to know, and that's where we've been working on writing structures, given the name, okay? And then from that, we can assign to it a particular intramolecular force, okay? Now, to write the structure, you may need to use the Lewis dot structure at first to figure out what it is, okay? And remember the Lewis dot structure? We went and counted all the valence electrons, okay? And then ammonia had the nitrogen is the central atom, and the hydrogens are bonded around it. But I've used ammonia multiple times. I'm hoping that now you understand or at least know what the structure is for ammonia, and that is as follows. All right, that's ammonia. And then fluorine is diatomic, so it's a real simple single bond between two fluorine atoms, okay? Being diatomic, that means that fluorine is nonpolar. And being nonpolar, we can assign to it the only force that's involved here is London dispersion forces for fluorine. So it has the weakest forces, okay? Weakest force, I should say. Now, ammonia, given here, you can use the fact that it's got a lone pair to tell you, I got a polar molecule. Remember, anytime you end up with a lone pair on the central atom, 100% of the time, I got a polar molecule. Okay? Now, what force to assign to it? Well, since it's polar, it's not going to have, we can eliminate London dispersion forces, so that's not the case. We can eliminate the ion dipole, okay, because there's no mention here of ions. So what's left is dipole-dipole or hydrogen bridging, okay? We will assign to it, yes, there's a dipole here, but we also know, hopefully, that we have hydrogen bonded to nitrogen, which is that special dipole where you have hydrogen bonded to those three atoms, nitrogen, oxygen, and fluorine, which results in HBF being assigned to ammonia. So dipole-dipole is not the one, okay? So we've assigned one, we know it's polar, we assign the polarity of the molecule. From that information, then we assign the intramolecular force, and then we make a note of London forces is the weakest, and hydrogen bridging is the strongest when we compared those three forces. No mention here of ion dipole. You can't really do any comparison with molecules with respect those molecules that have ion dipole, okay? Just those three forces, London dispersion forces, dipole-dipole, and hydrogen bridging. All right, so we've done that. Let's clear this up. There's the structures. There's the assignment of the particular force, okay? Now, again, we can only do a relative comparison. We're not giving absolutes and say, hey, this is the boiling point to the exact number. All we're saying is this one will have a higher boiling point than this compound, or higher viscosity than this compound, based on the intramolecular force that's been assigned. Okay, question. So number one, who has the stronger IMF? Okay, ammonia or fluorine? What do you think? Ammonia, exactly. Ammonia has a higher IMF, okay, which, keep in the back of your mind, when you look at the other species, which is London forces, that also suggests that ammonia would have a higher boiling point, okay, because it has a stronger IMF. All right, which has a lower boiling point. So the lower boiling point between the two will be the one with the weaker intramolecular force. So fluorine would have the lower boiling point, whereas ammonia obviously has a higher boiling point because it has a stronger intramolecular force. Fluorine has the weaker London force, which gives it a lower boiling point. Which one is polar? We talked about that. Ammonia is polar. The diatomic, all diatomics are non-polar. Okay, who would have the higher vapor pressure? What do you guys think? Who would have the higher vapor pressure? Let's say we put ammonia and fluorine in the closed container. All right. Who would have a higher vapor pressure? Ammonia or fluorine? Any ideas? But to answer that, ask yourself, who's got the weakest force? Fluorine or ammonia? No takers? Fluorine. Fluorine would have the higher vapor pressure, okay, because it has the weaker force. And so more of it would be in the gas phase, right, than ammonia. Which is the least viscous? Well, again, that would be the one with the weaker force, which would be fluorine. And then the surface tension would be ammonia. Ammonia will have more surface tension because it has the stronger force. So if we had liquids of fluorine and liquids of ammonia, the ammonia would beat up more than fluorine, okay? All right, this here kind of puts it together. As we increase the IMF, the viscosity goes up, okay? As the IMF goes from London, dipole to hydrogen bridging, the molecule that has that force assigned to it, the viscosity increases, gets thicker, okay? All right, which you can infer even the backwards. So we can infer, well, we can infer a lot of things, but you know, you can see that honey is a lot more viscous than water. You know, both of them are assigned, what that suggests is the intramolecular forces for honey are much stronger than the forces in the water. And that's why honey is a lot more viscous. The boiling point also increases because it's going to require more energy. Remember that the experiment we had a plateau. All that energy was being used to break up those intramolecular forces between the molecules so they can separate and go into the gas phase, okay? And then the surface tension increases for the same reason. Again, the molecules are being held on to each other tightly. but then our vapor pressure drops. Because since all the molecules are being held on tightly, there's going to be less molecules being allowed to be released to go into the vapor phase. Okay. All right. Not much to say about water here. Just want to throw that in. But water, we talked about this before when we were doing the Lewis-Dot structures. But that is the structure for water. Okay, it has two bonding pair and two non-bonding pair, or we call lone pair. Okay, very, very polar. It has a bent molecular geometry. This compound will dissolve literally anything, anything that's polar. Even those molecules that are classified based on the solubility rules, let's call it insoluble. Remember, there's always a little bit that is soluble, and when you're dissolving water. Okay. All right. Water has a very strong hydrogen bridging force between the molecules, very strong. Very unique properties, very polar, has a high IMF, low vapor pressure, boiling point 100 degrees, melting point 0 degrees, has a high surface tension, and it has a unique property when it freezes, when it goes from a liquid to a solid, it actually expands. And so what that means is this, that if I have like 10 milliliters of liquid water, and then I freeze it and I measure its volume is now 10 plus, okay? Because it's expanded, which results in the density for same number of amount of water, the density of ice is much less. Remember, density is a ratio of mass over volume. If I take 10 grams of water in a liquid and I take that liquid, it has 10 milliliters of water, weighs 10 grams. When I freeze it, it's going to still be 10 grams, but its new volume be 10 plus. So that ratio changes. It's 10 plus in the denominator. That means the density gets smaller, becomes less than 1. That means that for ice, it will float because the density changes, okay? Gets less than 1. Some crystals, structures of water. To the left, molecular crystal of ice. That 6-member structure is very common in nature, very extremely common. All right, so we talked about this in the lab, where we have the heating curve, where we take a solid, and the solid goes to a liquid, and the liquid goes into the gas, and we have a couple of plateaus, okay? And so at the heating curve in the far left, as we start to heat a solid, in this example could be ice, like we did in the lab, as we give it heat, we give it energy, it's still solid as it goes up until it hits the first plateau. On the first plateau, all that energy that it's absorbing, because you notice we're adding energy to it, is absorbing it. All that energy is being used to break up the intermolecular force of the solid, break it up, and causing it to go into the next phase, which is the liquid. When all of the solid has been converted, temperature goes up again, okay? And it's all liquid on the rise until it hits a second plateau. When it hits the second plateau, we have another plateau where the energy again is being utilized to convert all of that liquid into gas. And the intermolecular forces, if they're strong, it's going to take a lot of energy, and that boiling point is a little bit higher. See, normally for water, this is at 100 degrees. Some molecules require a little bit higher temperature. Then finally, when all that liquid has been converted to gas, then we have an increase in temperature again, okay? So be aware of that graph, be aware of where the solid is, where's solid, where's the change of phase from liquid to solid to liquid and liquid to gas, and so forth. Be familiar with that, this graph. During the phase changes, obviously, as I stated, the temperatures are constant. All the energy is being used to break up the IMF, not the bonds. And then you're breaking the IMF. It's important. We're not breaking bonds. It's very important here to know. We're not breaking bonds. We are breaking intermolecular forces. All right. Okay, congratulations. Guess what? We are done with chapter 14. Tell you what, let's take a quick break. All right, and we'll come back here and say 15 minutes and we'll continue. All right, so I got about 10 minutes till I come back about 5 after. All right. My background here, that was me 100 years ago. I got myself circled. Back away. I just found that picture. It had disappeared about 30 years, and I was able to find it recently. And yeah, that was me a long time ago. Anyway, we'll be back in 15. Okay, looks like we lost some people. Excuse me. Okay, it looks like, what time is it? 3. Okay. Well, this particular chapter is extremely short. Okay. And so what I want to do is just save this for Thursday. No, you know what? Let's just go through it, and then Thursday, I'll just open it up for questions, and we'll go from there. So it'll give you plenty of time to get, study it so you can do the exam. All right, so let's go ahead and just knock it out. All right, so in this particular chapter, we're dealing with solutions. So we're going to talk about coffee now. All right, so what exactly is a solution? A solution is basically defined as a solute dissolved in some type of a solvent, okay? And so basically, in essence, the solute is whatever chemical is present in the smaller amount, and the solvent is present in a larger amount. Now, the most common solution, or solvent, I should say, is water, but it's not limited to that. We always think of a solution as being a liquid, and not necessarily. It can be air, a solution of air. It could be even solid, and we'll talk about that in a minute. But in general, the majority of times we are dealing with water. But there are other solvents that we can utilize that are not water-based at all, okay, to make solutions. All right, now concentration is pretty self-explanatory. If you look at the glasses here on the far left, very light pink, far right, very dark color. So, and that is a function of concentration of the solute. And so on the far left, obviously there's less solute, which makes it a weaker, more dilute solution than on the far right. In fact, remember that color in the far left, that light pink color, because the lab we're doing tomorrow, we're going to strive to make a reaction to be that color rather than, anything to the right. So anyway, FYI. Okay, so types of solutions, okay? We can have a gas in a liquid. That's a solution, where carbonated soda, for example, is a classic example of that. Or we can have a liquid in liquid. So, here we go, vodka and tonic, for example, okay? A mixed drink, that's a good example of a liquid in a liquid. We can also take a solid and put it in a liquid if it's soluble. And so salt water, if we take sodium chloride and we put it in some water, well, we know sodium chloride is soluble, we're going to make a salt solution, okay? we could have a gas and gas, where air around us is a mixture of different gases. And then when we talk about a solid and a solid, a good example, classic example is steel. Steel is not iron by itself. Otherwise, it would just be called iron. But iron, pure iron, is not very strong. You really can't create or make buildings using steel, iron, pure iron. So what happens is iron is mixed up with carbon and maybe some different minerals, and it creates this very strong material that allows us to build buildings with that. Other examples, gold. A lot of golds that you have there are alloys, because pure gold in itself is very soft and sometimes doesn't render itself to be very good jewelry. So you want for a ring, you want a gold alloy that has other minerals in it to give it strength. Brass is a combination of copper and zinc. Okay, so there's a lot of mixtures of solids out there. Okay. Liquids, in liquids. The rule is real straightforward. Like dissolves like, and it goes back to polarity. So polar liquids dissolve in other polar liquids. Okay, so we have to learn the polarity. Okay, if a molecule that is polar, it will dissolve only in solvents that are polar. Like dissolves like. So polar solutes dissolve in polar solvents, whereas we have nonpolar solutes dissolve in nonpolar solvents. A good example of this, if you ever looked at it, is Italian dressing. Okay, Italian dressing, you have two layers. You have an aqueous layer, which is the polar part, and then you have an oil layer, which is a nonpolar part. Well, the aqueous layer dissolves some of the components of the Italian dressing because they exhibit a polar character, so they dissolve more in the water. And then there are components of that Italian dressing that are nonpolar, which obviously will not dissolve in water. So that's where the oil comes into play. It will dissolve in the oil. And so when you utilize Italian dressing, what do? You shake it up. And you're not really mixing it up. You're forming what's called an emulsion, because the oil and the water would never mix. They're just difference in polarity. But you can form like an emulsion, and then put that on your salad to enjoy the flavors of both the oil-based material and the aqueous-based material. Okay. Polar and non-polar do not mix. Italian dressing, like I mentioned, but a classical is that picture here on the left side, where the oil and water just creates a disaster because of the properties of the oil and the water. Now, when we talk about two liquids and we talk about whether we're going to mix or not, the term that is utilized is miscible. We tend to think of soluble, but when we have two liquids and they're both polar or both nonpolar, they will mix with each other, and we say they're miscible in each other. If they do not mix, then they're basically immiscible. Okay. When we deal with a solid and a liquid, we use the term soluble or insoluble. Okay, and that's what we got here. Solid means if it's a solid, we use the term soluble or insoluble. Majority of the time, we're dealing with aqueous systems. So the solubility rules play a big factor here to determine whether a material is soluble or insoluble. Okay. All right, so we have a table here. And what we do is, before we can answer the question is, will these solutes dissolve in these solvents? So in the first column, it represents the solvent. So that's going to be in greater quantity. And the solute is across the top. Okay. Well, before we can even answer this question, the first thing we got to do is define the polarity of the molecules. Okay. And we know that ammonia is very polar. And we talked about this. Okay, so NH3, which is ammonia, is a very polar compound. Okay, the next one is C12H12. Remember what I said about compounds that contain nothing but carbon and hydrogen with respect to their polarity? Do you recall? What, are they polar or non-polar? C12H26.
Polar.
Remember the polarity of the carbon-hydrogen bond? Even though they're different, remember what I said, that that bond is considered to be
Non-polar.
exactly nonpolar. So when you have a molecule of C12H26, nothing but carbon and hydrogen, what does that suggest as far as polarity? Polar, nonpolar.
Non-polar.
Exactly. And so we have a nonpolar species, C12H26. Then we have Br2, which is diatomic, okay? And being diatomic, polar, nonpolar. You guys you remember? All the diatomic molecules, there's 7 of them. Are they polar or nonpolar?
Non-polar.
Exactly. Okay. So now we have we define the polarity of the solvents. We have to do the same for the solutes. HCl, okay, we have 2 different atoms bonded together. Unless they're carbon and hydrogen, then automatically HCl is a polar molecule. Okay, automatically. It's that example I've used before where I have an A bonded to A and A bonded to B. The fact that A and A are the same is a nonpolar bond. Okay. The fact that A and B are different elements, automatically differences in electronegativity. We got a polar bond unless it's carbon hydrogen. Okay. Here we have HCl. If you forgot that it is a polar species, automatically look at it and say, well, I got 2 different atoms. It's a polar species. Okay. Then we have iodine, which is again diatomic, which, as the case of bromine, is nonpolar. Okay. Now we have the PCl3, the phosphorus dichloride. Okay. In order to determine, because this might be the first time you see that molecule, in order to determine this, we have to figure out the Lewis dot structure on it. Okay. And then the way we do that is go back. You may need to use determine the Lewis dot structure on that, or I'll show you something else here in a bit that'll help you. All right. We see that phosphorus has, let me change the color. It's hard to see. Phosphorus is a central atom, okay? Phosphorus has 5 valence electrons. There are 3 chlorides, okay? Each one brings 7 electrons, valence electrons. So that means there's 21 valence electrons coming from the chlorides. Remember how we did that? We have a total of 26 valence electrons, 5 from the phosphorus, 3 from the chloride. And that's divisible by 2, so I have 13 pair, okay? Phosphorus is the central atom, so I can very quickly draw phosphorus and then 3 bonds to do 3 chlorides. That takes care of 3 of them, so I got 10 of them, 10 pair. All right, so as I stated before, I always start in the outside atoms and fill the octet. So I just go around and I go 1, 2, 3, 4, 5, 6, 7, 8, 9. So that took care of 9 electrons pair. I got 1 left, okay? I cannot put any more on the chlorides because the octet is fulfilled. And now the only place to put the last one has to be on the central atom, which is the phosphorus. I just put a couple of dots there. Okay, that is analogous to ammonia. If you recall the structure that we came up with ammonia. And remember what I said about the lone pair? What does that tell you automatically about the polarity of PCl3? We have a lone pair in the central atom. Is PCl3 polar or nonpolar? What do you guys think? Well, think about it. You know, you got phosphorus and chloride. Are those two the same atoms? No, they're different atoms. So
Non-polar?
no, let's think this through. Okay, we have phosphorus bonded to 3 chlorides. Okay, take a look at 1 phosphorus and 1 chloride. Is that represented AA scenario or AB scenario?
AA.
Are you sure? Remember, AA represents the atoms of the same. A bonded to A versus A bonded to B. Okay? Isn't that
AB.
exactly AB? So you got phosphorus and chloride. What does that tell you about the polarity of the bond between phosphorus and chloride? The fact that they're different.
Polar?
You got polar, exactly. Furthermore, you got 2 more. So you got 3 polar bonds. Then on top of everything, you have a lone pair that's a bad drawing, but you get a lone pair in the central atom. Remember what I said about lone pairs in the central atom all the time? Polar, nonpolar.
Non-polar?
No.
Oh,
Polar. Remember, like ammonia, look at ammonia over here. Ammonia has a lone pair in the central atom. Everybody that has a lone pair in the central atom. Water has 2 lone pairs in the central atom. Okay? 2 lone pairs, polar molecule. Whenever you come up with the Lewis dot structure and you got a lone pair in the central atom, you don't have to go any further. You can automatically say, I got a polar molecule. Okay? Got a polar molecule. So PCl3, like ammonia over here, NH3, is polar. In fact, what is the common factor between, what does phosphorus and nitrogen have in common with respect to the periodic table? They're both in the same group. And being in the same group, when they make formulas as compounds, they're going to have the same type of structure. Okay? They're going to have the lone pair in the central atom. So PCl3 is polar. Okay? What about CH4? Polar, nonpolar?
Polar.
non-polar?
I heard polar and something else.
Non-polar.
Non-polar, exactly. Okay. Carbon-hydrogen bond, just like the C12H26. When you see nothing but carbon-hydrogen bonds, automatically non-polar. Okay. So now that we defined the polarity of the solute and the solvent, now we can determine whether they're going to dissolve in each other, keeping in mind that like dissolves like. Okay, it's analogous to, I use the example a lot with makeup. There's some makeup that's water soluble, correct me if I'm wrong, that you can remove with just soap and water. Okay, but then there's some makeup that you need an oil-based cleanser to remove. Okay, and being an oil makes it non-polar. So what does that suggest about that particular makeup? It is non-polar. For that other makeup that just uses soap and water, that suggests that the character of that makeup makes it polar because it dissolves in water. Okay. So here, once we define the polarity, now we can determine whether something, the solute is soluble in the solvent based on the polarity. So if we take hydrochloric acid, HCl, and we mix it in ammonia, yes, we will get it to dissolve and it will be soluble because they both share the same polarity. If we take iodine and we dump it in ammonia, no, they won't dissolve. Why? Because I have a nonpolar iodine trying to go into a polar solvent. But PCl3 will dissolve in ammonia. Okay. Remember, the solute is what's in lesser amount and lesser quantity than the solvent. So PCl3 will dissolve in ammonia because they both share the same polarity, but methane will not. Okay, methane, because it's nonpolar, that's what methane is, carbon CH4. Since I got a nonpolar and a polar solvent, there's going to be no solubility. If I take the hydrocarbon C12H26 and I try to add hydrochloric acid to it, there will be no solubility going on because HCl is polar and C12H26 is nonpolar. Okay, but it will dissolve iodine because we share the same polarity. It won't dissolve PCl3, okay, because they have differences in polarity, but methane can go into it no problem because they're sharing the same polarity. Bromine and HCl, that'll be a no, differences in polarity, but it will dissolve some iodine, okay? Because they both share the same polarity. It won't dissolve the PCl3, but it will dissolve some CH4, again, because they share polarity. All right, so in order to be able to answer questions like this with respect to solute and solvent and to determine whether it is soluble or not, the first thing you got to do is to define the polarity of the molecule and the solvent. Once you do that, you use the rule as like dissolves like. Polar solutes dissolve in polar solvents. Non-polar solutes will dissolve in non-polar solvents. The two do not mix, okay? They just won't mix. And think about it, if you were to, heat up some butter, you're cooking something on the oven or on the stove, and you melt some butter, and you got it all melted down, and you add water to that butter. They're not going to mix. Butter is very nonpolar. And the water, try this at home. Try this so you can see for yourself. And it won't mix. If you take that butter and you throw salt in it, that sodium chloride won't dissolve because you have an ionic compound, which is very polar, and then a nonpolar butter material, okay? But if I'm boiling water and I throw in the sodium chloride, boom, that sodium chloride dissolves very readily, okay? So it's all about polarity. Now, with respect to liquids and how they mix or not mix, here, remember, if they're liquid and liquid, it's either miscible or immiscible. And pretty straightforward here to answer these questions, because again, whether something is miscible or not depends on the polarity. So a polar liquid and a polar solvent, since they're both polar, they will mix. So we say they're miscible, but immiscible if we have a nonpolar solvent. The converse is also true. Nonpolar liquid, polar solvent, immiscible. Miscible when they are both the same polarity. Polar solid, okay? Polar solid in a polar solvent should make it soluble, okay? And insoluble in a nonpolar solvent. A nonpolar solid would be insoluble in a polar solvent, okay? But very soluble in a nonpolar solvent. An ionic compound like sodium chloride, well, with respect to solubility in the polar solvent, which goes away, would have to be water, okay? we have to check the solubility. And definitely insoluble in the non-polar salt. Okay, let's talk about concentration. There's two types of concentrations that we're going to work with. One is the mass percent, okay? And the other one deals with molarity. Now you got a taste of molarity yesterday when we were using hydrochloric acid, okay? Hydrochloric acid, remember I said its concentration was 3 capital M. That was called molarity. It has the units of moles per liter. Right now, how do we calculate the mass percent? Okay, well, we take the mass of the solute and we divide it by the mass of the solution. Keep in mind, the solution is the total mass of the solvent and the solute, and not just the solvent. And that's where the error sometimes occurs because students don't take into account. Here we're talking about a solution. Remember, by the definition, a solution consists of a solute, which is in lesser concentration, and a solvent. Whether this is aqueous or non-aqueous makes no difference, okay? So let's calculate the mass percent if you take 15 grams of potassium nitrate. Now here, we don't care what the chemical is. It could be any chemical. So we don't really need the structure of the chemical at all. All we need to know is the mass of the water, in this case, and the mass of the solute. So we're going to take 15 grams of potassium nitrate, and then we're going to dissolve that in 135 grams of water, okay? And we know it's going to dissolve. Why? Because we're using potassium. And if you refresh your memory in the solubility rules, potassium is part of the big four I talked about, number 1 in the solubility column. So anything with potassium is soluble. All right, so we take 15 plus 35, all right, in the denominator, we got 15 in the numerator. Potassium nitrate is the 15 in the numerator, and it's also in the denominator plus the amount of water, and times 100 says we have a mass percent of a 10% solution. If we take 15 grams of potassium nitrate, the solute, and we add it to 135 grams of water, okay, got a 10% solution. And that's the straightforward type of calculation. You're given the solute, the weight of the solute, the weight of the solvent, and you just plug in the numbers and you're good to go. Occasionally what happens is you need to calculate how much water, you know the percent that you're trying to make, you know how much of the solute you have, and you need to calculate, well, how much solvent do I need to make that percent solution given that amount of solute, okay? And that's the next type of problem. So in this case here, we have how many grams of water? We don't know what the water is, which is the solvent, okay, the solvent. If are needed to make a 5% solution, if I start off with 10 grams of salt, okay? Could be any salt, any ionic compound. And so we set the problem up like we normally would. We got the solute on the numerator and the denominator, but since we don't know how much water we need, we got we have an algebraic expression. We define the amount of water as X, which means we need to solve for X, okay? Now, the problem looks complicated, but it really isn't. We're going to break it down, okay? Now, with respect to algebra and solving for X, there's a few ways to solve for X. Not one way is correct over the other, okay? This is one way to do it. Makes no difference how you do it as long as you get to the answer, okay? So we have that algebraic expression. We're solving for X, and we get this expression. Well, how did they get from there to there? Well, what they did is, notice that 10 plus X is in the denominator. So what they did was, let me change color a little bit. They multiplied on both sides. Oh, that's not right. Let's go red. On both sides, they multiplied 10.0 plus x on both sides of the expression. 10 plus 0 plus x. And notice when that occurred, this canceled with this, leaving us with 5.0 times 10 plus x, which is right here, and then 10 times 100, which is right there, okay? Now, at this point, you can go multiple directions, okay? Not one direction is right, you were wrong. You can expand this on the left, 5 times 10 or 5x, and then put all your numbers in one side and solve for x. That's one way to do it. They tend to go a different route, the book, I mean, and so they come here. And all they did here, we just multiplied 10 times 100, which gives you 1,000, okay? Then they came, the next expression was as follows, okay? Well, what they did here was simply divide on both sides by 5. Okay, so the 5s cancel on the left, leaving you with 10 plus x, and it's 1,000 divided by 5. And that is 10 plus x equals 200. Okay, now you can solve for x, and you can go, move 10, subtract 10 from both sides of the equation to give you 190, okay? Now, they put it in scientific notation simply because of the sig figs. We got 3 sig figs over here. And since you end up with 190, in order to make 3 sig figs, you put it in scientific notation and give you the 3 sig figs. Now the question is how do I know that number is correct? Well, what you do is you take the 190 and you put it back into the original equation, okay? And then do the math, and you should end up with 5.00 equals to 5.00, which is a true statement. If you don't end up with 5 equals 5, then you got some other number, then that's not a true statement, so go back and check your math, okay? So what this means is this: if you take 10 grams of a salt, and then you add 190 grams of water, okay, you will end up with a 5% solution. Which, by the way, I'm sure for you nursing students out there, a 0.09% saline solution. Okay, you can calculate, you can make it like this, but this is nothing more than sodium chloride made up to be 0.9%. Okay. And you can do calculations if you ever need to make a 0.9% solution of sodium chloride. Hopefully you don't ever have to do that out in the field, but you never know. Okay. Anyway, it's 0.9% for a specific reason. All right, let's move on. Any questions right now about this? Okay. This is checking that your answer, you're making sure your answer is correct. All right, now with respect to molarity, molarity has the units of moles of solute divided by the liters of solution. The fact that you have moles means that you need one. If you're given the form, given a name, you have to write the formula. Why you need the formula? Because you need a molar mass. Most of the time you're given, I take X grams of some compound, I dissolve it in X liters of solution. What is my molarity? Well, you have to determine what the formula is for that compound, which then you determine the molar mass, which then allows you to calculate how many moles. Okay. Note that the units are in liters. It's moles per liters. Okay. If the problem gives you the volume in milliliters, then simply convert it to liters. Okay. You don't want to divide it by milliliters because your answer will be incorrect. Moles per liter. All right. For example, calculate the molarity if 9.99 grams of potassium bromide is dissolved in water to make 2.5 liters of solution. Okay, so this is where we need to figure out the formula first. And this is where we've been working with up to this point here, figure out the formula. We got potassium, and it's potassium bromide, which tells me and should tell you that we're dealing with an ionic question. Ionic compound. And so potassium is in group 1. So potassium has a +1 charge when it becomes an ion. And the bromide is in group 7, so it has a -1. Okay. So now I can put these together on a 1-to-1 ratio because I got a positive and a negative. So the formula for potassium bromide is simply KBr. With that information, I go to the periodic table, find the atomic weight for potassium, find the atomic weight for bromide, and then that gives us the molar mass, which is 119. Okay, so recall, when you go back to that flow chart I had given you a while back, last chapter, where you have grams, you want to get to moles. So if I got grams, I need to get to moles, I divide by the molar mass. So here I divide 9.99 grams and I divide it by 119, okay? The other aspect is this. When you do your math, just make note that you have 9.99 grams and 2.50 liters. In both cases, you have 3 sig figs. So your answer should be in 3 sig figs eventually. So in between all that, don't truncate the numbers. Keep the numbers, whatever your calculator is. If it shows 3 digits, keep with 3 digits. If it shows 15, continue with whatever number of digits your calculator has. It is only at the end of the mathematics that then you truncate and write your answer with the correct sig figs. All right, so if you take 9.99 grams and divide it by its molar mass of 119, you have 0.08395 moles. Okay, notice nothing was truncated. Since we're dealing with liters, we can straightforward just divide it by 2.50, and we results in a molarity of 0.0336 moles per liter, or capital M. The molarity of potassium bromide of 9.99 grams dissolved in 2.50 liters is 0.036 moles per liter. Okay. So now with a solution with the X amount of concentration, I can take an X number of moles of that material like we did yesterday in the lab. Remember, we took a 3 molar solution and we took out 10 milliliters. That allows us to calculate how many moles of acid, HCl, we actually utilize in the experiment. So one advantage of making solutions of a known concentration like this, the molarity, by taking the volume out, we can get an X number of moles or whatever we want that to react with, okay? All right, so, we got questions, in the textbook, and there's a practice sheet. So I would practice with these calculations. It looks like Thursday will be a study day. So if you have questions, be it the lecture, be it the lab, feel free to bring them in on Thursday and next Tuesday. Okay, we do have a final coming up, so good time to bring questions. Let's do one more, okay? First, it says calculate the molarity if 5.0 grams of sodium phosphate is dissolved in water to make a 255 milliliter solution, okay? So first things first, we need a formula. Sodium phosphate. Now we've got phosphate. Hopefully by now you know that I can go to the polyatomic ion table and see that that is the structure for sodium phosphate, okay, as a -3. Plus, sodium is a group 1 metal, so it has a +1, okay? It's a group 1 metal. It's going to lose that 1 electron, resulting in a +1. That means that I need 3 sodiums for every phosphate. So the formula for sodium phosphate is Na3PO4, okay? So now with that information, I can figure out the molar mass. I got 3 sodiums, I got 1 phosphorus, and 4 oxygens. Find the molar mass for each atom from the periodic table, multiply by the number of each atom, tally it up, you end up with the molar mass, okay? Now the other aspect is this. The solution is 255 milliliters, which is good. Okay, no problem, but we're in the units of milliliters. Remember that molarity has the units of moles per liter. So we're going to need to convert those milliliters to liters. And we know that there are 1,000 milliliters is equal to 1 liter. Okay, so here's a conversion factor right there. All right, so with that information, we can set up the problem. And we have a molar mass of 163.94 for sodium phosphate. We're taking 5 grams of sodium phosphate. We're going to divide by the molar mass. Remember, we start off with grams. We're going to get 2 moles. We divide by the molar mass. So that represents 0.0304996. Okay. Moles. Then 255 milliliters, we're converting that to liters. You can use that conversion table there, or just recognize that you can move the decimal point over 3 positions and you're at the liter units. Okay. Now you divide through. Remember, look at this, the number of moles, nothing was truncated. I'm using all the digits there. Okay, so I'm taking that, dividing by 0.255. Note that my starting sig figs is 5.0, which is 2, 255, which is 3. So my answer should have 2 sig figs. Okay, so if I take 5 grams of sodium phosphate and I dissolve it in 255 milliliters of solution, the molarity of that solution will be 0.12 moles per liter. Okay, there you go. So yeah, of course, don't forget the assignments. There is a practice exam on the website. All right, other than that, we are done. Okay. We are done with all the chapters. We did do chapter 16 in the lab, okay? Don't forget about that homework. Keep in mind also, I